Right now, the device you're using to listen to this is locked.
Even if the screen is on.
Yeah, even if the screen is on, deep inside its memory, it's being guarded by an invisible, impenetrable number.
A number that is, millions of digits long.
Right. And if someone wanted to break in, the laws of physics themselves would stand in their way.
They literally would.
Welcome to Science After Dark. Wherever you are tonight, just, dim the lights, take a deep breath, and settle in for a calm late-night exploration.
Because tonight we are looking at something so fundamental, you've known about it since you first learned to count.
Prime numbers, the atoms of arithmetic.
It really is the perfect topic to unwind with, I think, because there is something deeply grounding about primes.
How so?
Well, they're completely independent of human invention. Like, if the universe were to disappear tomorrow, the prime numbers would still be exactly what they are.
They're a fundamental truth. And our mission on this deep dive is to figure out how something as simple as counting can lead to, well, the deepest unsolved mysteries in the cosmos.
And more importantly, how these ancient numbers are secretly working behind the scenes to secure your entire modern digital world.
Yeah, your banking, your emails, everything. So let's start at the absolute bedrock. What exactly makes a number prime?
So the foundation begins with a very specific definition. A prime number is a whole number greater than one that has exactly two distinct positive divisors.
One and itself.
Exactly. If you picture a number line and just start walking up it, you hit them almost immediately.
Starting with 2.
Right, 2, which is completely unique as the only even prime number in existence. Then 3, 5, 7, 11, 13, 17, and so on.
They are the numbers that just cannot be broken down or divided into smaller integers.
All right, they're irreducible.
But hold on, I have to stop you right at the definition there. Why is the number 1 excluded?
Ah, the famous exclusion of 1.
Because, if a prime is a number divisible by 1 and itself, the number 1 fits that perfectly. It's divisible by 1 and it's divisible by itself. It feels like an arbitrary rule to just kick it out of the club.
It does feel arbitrary at first glance, but excluding the number 1 is actually a matter of protecting the entire hidden architecture of mathematics.
Protecting it from what?
Well, we exclude it to preserve something called the fundamental theorem of arithmetic. This was formally and rigorously proven by Carl Friedrich Gauss back in 1801.
Okay.
And what it states is that every integer greater than 1 can be expressed as a product of prime numbers in exactly one way.
Okay, so you mean if I take a composite number, like, say, 60, the only possible way to build it out of primes is 2 times 2 times 3 times 5.
Yes, exactly. That is its unique fingerprint.
Right.
Now think about what happens if we let the number 1 be a prime number.
Oh, I see where this is going.
Yeah, that unique fingerprint is suddenly destroyed. 60 could be 1 times 2 times 2 times 3 times 5.
Or it could be 1 times 1 times 1, 1.
Exactly. You could just keep endlessly stapling ones onto it. A single number would suddenly have an infinite number of factorizations.
The whole structure would just dissolve into chaos.
The rigid, elegant structure of arithmetic would just completely collapse, yes.
I see. It's a lot like the periodic table of elements.
Oh, that's a good comparison.
Right, because in chemistry, every molecule is a specific arrangement of atoms. Primes are the indivisible atoms, and every other number is a unique molecule built directly from them.
That is a brilliant way to picture it, yeah.
If the number 1 was an atom, it would be this weird, ghostly element that you could just infinitely attach to any molecule without actually changing what the molecule is. It would just break the rules of chemistry.
It would ruin the whole system. And just like chemists mapped the elements, mathematicians have spent centuries trying to map these prime atoms.
Which is a huge undertaking.
To understand the first great leap in that mapping, we actually have to travel back in time to ancient Alexandria around 300 BCE.
Okay, so we're talking about the era of Euclid.
Yes. Euclid compiled a 13-book treatise called the Elements, which essentially served as the standard math textbook for the next 2,000 years.
Wow, 2 millennia.
Right. And tucked away in Book 9 of that text is a proof so elegant that it is still taught today. It's the canonical demonstration that there are infinitely many prime numbers.
But wait, Euclid didn't have supercomputers. He didn't even have modern algebra, right?
No, not at all.
How do you definitively prove that something goes on forever just by using ancient geometry and logic.
You do it through a masterpiece of indirect reasoning. Euclid essentially sets a logical trap.
I love logical traps.
He asks the reader to imagine the exact opposite. Assume, just for a moment, that there is a finite list of prime numbers.
Okay.
Let's say you could gather every single prime in the universe and, I don't know, put them in a bag. 2, 3, 5, 7, all the way up to some final massive largest prime.
Got it. I'm picturing the bag.
Euclid says, take every single prime on that complete list and multiply them all together to create one giant supernumber, then add exactly 1 to it.
Okay, I'm tracking. We've built this new, unimaginably huge number.
Now, try to divide this new supernumber by any of the primes from your original list. What happens? Because we added that +1 at the very end, every single division will leave a remainder of 1.
It will never divide cleanly.
Exactly.
Because it's always exactly one step away from being a multiple of any of those primes.
Right. So there are only 2 logical possibilities left. Either this massive new number is itself a prime number, or it is divisible by some other mystery prime that was not on your original list.
Right.
Either way, that finite list you started with was incomplete. The primes must go on forever. It's an inescapable contradiction.
That is a beautiful conceptual trapdoor. You can grasp that lying in the dark at just running the logic in your head.
It's pure thought.
But, proving they go on forever is one thing, actually locating them in the wild is another. Which brings us to another brilliant mind from the Library of Alexandria, roughly a generation later in 240 BCE.
Ah, yes. Eratosthenes of Cyrene.
Famously known for being the first person to calculate the Earth's circumference.
He was a genius, and he also gave us a tool called the Sieve of Eratosthenes.
Which is such a satisfying algorithm.
It really is.
If you want to find primes, you just write down all the numbers starting from 2.
Okay.
You circle 2, because it's the first untouched number, making it prime.
Right.
But then you sweep through the rest of the list and cross out every multiple of 2, 4, 6, 8, 10, because obviously they can't be prime.
Since 2 divides them.
Exactly. Then you move to the next uncrossed number, which is 3. Circle it, sweep through and cross out all multiples of 3, and you just repeat this process.
Yeah, the numbers that slip through the sieve, the ones left standing, are your primes.
It is a conceptually perfect mechanism.
It is. But this brings us to a fascinating threshold in our deep dive. We know the primes go on forever. We know how to mechanically sift them out. But as you count higher and higher into the millions and billions, a deeper mystery emerges.
The rhythm.
Yes. Are these numbers appearing to a predictable rhythm, or are they scattered completely at random?
Intuitively, you'd think they get rarer, right? Down in the single digits, they are packed tightly together. 2, 3, 5, 7. But as the numbers get astronomically large, the gaps between the primes must stretch out.
They do stretch out on average, but here is where it gets maddening for mathematicians.
Why?
They never, ever settle into a predictable rhythm. You might be scanning through massive numbers and find a gap of 1 million composite numbers without a single prime.
Wow.
And then suddenly you stumble upon 2 primes sitting right next to each other.
What's wild?
This intense tension between apparent randomness and a suspected hidden cosmic order that is the central drama of analytic number theory.
Which brings us back to Carl Friedrich Gauss, but this time in the 1790s. And he's just a teenager at this point.
Just a teenager, yes.
Sitting by lamplight, privately poring over vast tables of prime numbers.
Yes, young Gauss noticed a profound pattern hidden in that raw data. He conjectured that the density of primes near any given number, let's call that number n, seemed to be approximately 1 divided by the natural logarithm of n.
Okay, so a logarithmic curve.
To put it plainly, the total number of primes less than n is roughly n divided by the natural logarithm of n. Adrien-Marie Legendre actually published a similar conjecture independently in 1798.
It's astounding that a teenager could just eyeball raw data and see a logarithmic curve.
It takes a special kind of mind.
But again, guessing a pattern and proving it mathematically are vastly different beasts.
Incredibly different. It took an entire century to prove this observation mathematically.
100 years?
Yeah, it became known as the prime number theorem. It was finally proven in 1896 by 2 mathematicians working completely independently, Jacques Hadamard and Charles-Jean de la Vallée-Pousset.
Wow, they were both on the same track.
But to prove it, they couldn't just use basic arithmetic. They had to rely on what would become the most famous object in all of mathematics, the Riemann zeta function.
Okay, let's unpack the zeta function, because this is where pure math starts to sound like magic. Leonhard Euler originally created it in the 18th century, right?
He did. Euler showed that an infinite sum of fractions could actually be rewritten as a product over all the prime numbers.
It was a stunning bridge.
It was. It essentially connected the smooth, continuous world of calculus with the discrete, chunky, unpredictable world of prime numbers.
But it was Bernhard Riemann in 1859 who truly weaponized it.
Yes. In a single, dense 8-page paper, he linked the distribution of prime numbers directly to the zeros of this complex function.
Okay, I'm going to need you to translate that. If you're lying there listening right now trying to picture this, what are these zeros and what does the Riemann hypothesis actually claim?
Okay, think of the distribution of primes as a complex, chaotic sound wave.
Okay, chaotic noise.
Right. What Riemann did was essentially build a mathematical prism. When you pass that chaotic prime sound wave through his zeta function, it splits the noise into pure individual frequencies.
Wow.
The zeros of the function are those specific pure frequencies. Riemann conjectured that if you plot all these non-trivial zeros on a graph, specifically on the complex plane, they don't scatter randomly.
Where do they go?
They all line up perfectly on a single, infinitely long vertical line. Specifically, the line where the real part of the number equals exactly 1/2.
So out of all this apparent randomness, the underlying frequencies of the primes form a perfectly straight line.
Exactly. If the Riemann hypothesis is true, it means that the prime numbers are distributed as regularly as mathematically possible.
That's incredible.
It means the apparent static or error in the prime number theorem is as small as it can possibly be. It is the ultimate hidden rhythm of the universe.
And we know it's at least partially true, right? Because we've thrown supercomputers at it.
We have. We have calculated the first 10 trillion zeros of the zeta function.
10 trillion.
And every single one of them falls exactly on that critical vertical line. Not a single deviation.
But in pure mathematics, checking 10 trillion examples doesn't prove it will hold true for infinity.
Because infinity doesn't care about 10 trillion.
Right. And the stakes here are very real. In the year 2000, the Clay Mathematics Institute designated the Riemann hypothesis as one of its 7 Millennium Prize problems.
The ultimate bounty.
Yeah, they placed a $1 million bounty for a correct mathematical proof. Over 2 decades later, that prize remains unclaimed. It is arguably the greatest open problem in mathematics.
It really is. But, while some mathematicians are staring at the infinite horizon trying to prove this cosmic pattern, others are zooming in.
Looking at specific numbers?
Yeah, they are dedicating their lives to hunting down individual giants in the prime landscape, the massive outliers.
The Mersenne primes, named after Mersenne, a 17th century French monk.
Yes, those ones.
These are primes that follow a very specific formula, 2 to the power of p minus 1, where p itself is a prime number.
Let's do a small one just to visualize it. 2 to the power of 3 minus 1. That's 8 minus 1, which is 7.
And 7 is a prime number. Right. Or 2 to the power of 7 minus 1, which is 127, also prime. But why are mathematicians so obsessed with this specific formula?
Well, it comes down to how computers think. Computers operate in binary, right? Zeros and ones.
Right.
A Mersenne prime, because it is a power of 2 minus 1, looks like a solid, unbroken block of ones in binary.
Oh, that makes sense.
Think of how the number 999 is just a solid block of nines in our decimal system. Because of this unique binary structure, computers can test if these numbers are prime using the Lucas-Lehmer test.
And how's that different from just dividing the number normally?
Normal division takes an enormous amount of processing power for massive numbers. The Lucas-Lehmer test bypasses heavy division entirely.
Oh, really?
Yeah, it uses simple addition, subtraction, and shifting bits around, which computers can do blazingly fast.
That is why, if you look at the record books for the largest known prime number, it is almost always a Mersenne prime.
Exactly.
Which leads to this massive global hunt. In 1996, George Woltman founded GIMPS, the Great Internet Mersenne Prime Search.
Such a great acronym.
It utilizes the idle processing power of thousands of volunteers' computers all over the world to test these giant candidates.
And it yields incredible results. Like, on December 7th, 2018, an electrical engineer named Patrick LaRoche made an awe-inspiring discovery using GIMPS.
What did he find?
He found the largest known prime number to date, 2 to the power of 82,589,933 minus 1.
The scale of that is just mind-bending. To visualize this for you listening, this single prime number has 24,862,048 digits.
It's hard to even picture.
Yeah, if you were to print this one number out in a standard book font, it would fill roughly 9,000 pages.
Wow.
A 9,000-page book of just numbers. And it cannot be divided by anything other than 1 in itself.
It is staggering, and it's a beautiful contrast to a famous historical misstep by Pierre de Fermat in the 1600s. Fermat was a brilliant French lawyer who treated mathematics as a hobby. He conjectured that all numbers formatted as 2 to the power of 2 to the n plus 1 were prime.
The Fermat primes.
Yeah.
And he had a good reason to think so at first, didn't he?
He did. The first 5 numbers in his sequence worked perfectly, yielding 3, 5, 17, 257, and 65,537.
All prime.
All prime. Fermat thought he had discovered an unbreakable pattern. But in 1732, Leonhard Euler proved him wrong.
Euler strikes again.
Euler showed that the very next number in the sequence, which is 2 to the power of 32 plus 1, or 4,294,967,297, is not prime at all. It is composite.
It perfectly divides into 641 times 6,700,417.
A hobbyist dream crushed by history's most prolific mathematician.
And the wild part is that no Fermat primes beyond those original first 5 have ever been found.
Never.
But okay, we talked about the giants. Let's talk about the twins.
Yeah, twin primes. These are pairs of prime numbers that differ by exactly 2. 11 and 13, 29 and 31.
Right.
The twin prime conjecture asserts that even as you go to infinity, you will continue to find these pairs separated by just 2.
And this leads to what might be my favorite scientific underdog story of the century.
It's a great one.
For decades, mathematicians didn't even know if the gap between primes was bounded at all, or if they just eventually drifted infinitely far apart. Then, in April 2013, Yitang Zhang stepped into the spotlight.
Yeah, he wasn't a famous professor at a prestigious institute.
No, he was working in obscurity as a lecturer at the University of New Hampshire. And out of nowhere, he shocked the world by proving that there are infinitely many pairs of primes that differ by, at most, 70 million.
Which, to a layperson, a gap of 70 million sounds huge.
Right.
But mathematically, proving that a bound exists at all was a monumental, earth-shattering leap. It meant the primes don't just drift apart forever, they keep snapping back together.
And the mathematical community's reaction was beautiful. Through something called the Polymath Project, initiated by Timothy Gowers and heavily advanced by James Maynard, mathematicians from around the world collaborated online to shrink Zhang's bound.
They worked incredibly fast.
Yeah, they took his theoretical framework and rapidly chiseled that 70 million gap down to 4,680. Eventually, they got it down to just 246.
To prove the twin prime conjecture, they need to chisel it all the way down to exactly 2. They are agonizingly close.
It shares that maddening simplicity with Goldbach's conjecture, which originated in the 1742 letter to Euler. Goldbach proposed that every even integer greater than 2 is simply the sum of 2 primes.
And we've used computers to verify this up to 4 times 10 to the power of 18.
But as we know, checking isn't proving. Harold Helfgott managed to prove the odd version in 2013, showing every odd number greater than 5 is the sum of 3 primes. But the even version remains an open mystery.
It does. Now, if we pull back and look at the bigger picture, for thousands of years, everything we've discussed tonight was the purest form of pure math.
Yeah, just theory.
From ancient Alexandria to the 1900s, this was knowledge pursued entirely for its own sake. It had zero practical application.
Until the late 20th century, when suddenly these abstract atoms of arithmetic became the concrete bedrock of human civilization.
It was a massive shift.
Let's talk about 1977 at MIT.
This was the turning point. 3 researchers, Ron Rivest, Adi Shamir, and Leonard Adelman, created a public key crypto system that would become known by their initials, RSA.
Okay, we need to explain the mechanics of this, because RSA cryptography relies on a mathematical one-way street. I've heard this described like scrambling an egg. It's easy to scramble it, but impossible to unscramble it.
That's the core idea.
But that doesn't actually explain the math. Let's use mixing paint instead.
Okay, I like paint.
If I take a very specific unique shade of prime red and a unique shade of prime blue and mix them together, I get a massive puddle of purple paint.
That's easy to do.
Right, but if I hand you that bucket of purple paint and say, extract the exact original red and blue, you can't just undo it. You would have to test every single shade of red and blue in existence until you found the exact match.
That is an excellent analogy because it highlights the computational burden. In RSA, a computer takes 2 massive prime numbers, each hundreds of digits long, and multiplies them together. That creates a massive composite number, the purple paint. This number is made public. It's the lock on the door.
Ah, I see.
But to reverse engineer it to factor that massive number back into its two primes requires trial division that is computationally unfeasible.
But how does a public composite number actually lock a message? I've seen the name Fermat's little theorem thrown around here.
Yes, Fermat's little theorem, generalized by Euler, provides the mechanism. Imagine a mathematical clock where the number of hours on the face is a prime number.
Okay, a prime clock.
The theorem proves that if you spin the hand of this clock using a specific formula, the outcome is always completely predictable.
Right.
RSA uses this clock math called modular arithmetic to wrap a message in layers of mathematical spin. Anyone can use the public composite number to spin the lock shut.
But they can't open it.
Right. Because of how the clock math works, the only way to spin it backward and read the message is if you know the exact two hidden primes that determine the size of the clock.
And this isn't just theory. If you are listening to this on a Wi-Fi connection, or if you've ever bought something online, sent a secure email, or checked your bank balance, you're relying on this exact math.
Every single day.
Every time you see that little padlock icon in your web browser, your data is being protected by a 2048-bit RSA key.
And to understand the strength of that protection, if you tried to factor a 2048-bit key using the most powerful supercomputers on Earth today and the best-known factoring algorithms, it would take longer than the current age of the universe.
Just to crack one message.
Exactly. The simple fact that it is hard to factor large numbers is the invisible armor holding up the global economy.
But there is a storm on the horizon.
A very big storm.
In 1994, a mathematician named Peter Shor discovered Shor's algorithm. And this is terrifying because it involves quantum computers. How exactly does a quantum computer break this?
A classical computer tries to guess the prime factors sequentially, one after another, which is why it takes billions of years.
Like trying every shade of paint one by one.
Exactly. But a quantum computer uses quantum superposition. It doesn't test one answer at a time. Shor's algorithm creates a mathematical state where all possible factors are evaluated simultaneously as wave frequencies. Through quantum interference, the wrong answers cancel each other out, and the correct prime factors amplify each other and instantly emerge.
So if someone manages to build a large-scale, stable quantum computer capable of running Shor's algorithm, they wouldn't need the age of the universe to unscramble the paint.
They could do it in hours.
They could crack RSA and upend global digital security overnight.
Yes.
That is exactly why the brightest minds today are in a frantic race to develop post-quantum cryptography. We are literally racing to invent new math before our current math gets broken by new physics.
It is a profound trajectory if you think about it. We started in a quiet room in ancient Alexandria where Euclid logically deduced that primes go on forever.
Yeah.
We watched Eratosthenes sift them out and young Gauss search for their rhythm by lamplight.
And now, those exact same simple building blocks are the digital locks of the internet era, sitting at the center of a quantum arms race. They truly are the atoms of our reality. As we wind down this deep dive, I wanted to leave you with a thought to mull over as you drift to sleep. We've seen how something as seemingly innocent and elementary as counting integers holds universe-bending patterns. Patterns that have stubbornly resisted the greatest minds for thousands of years.
It makes you wonder.
It does. If the secrets of the prime numbers are still hiding in plain sight, what other elemental truths about our reality are sitting right in front of us, just waiting for someone to finally see the rhythm?
A beautiful question to leave on.
Thank you for spending your evening with us. Rest well, stay curious, and good night from Science After Dark.